Hey guys, so in this video we're going to go through differentiability and what it looks like graphically and what it looks like in an equation form with some AP multiple choice questions thrown in. It's going to be great. So we've learned about something called continuity previously in Unit 1. You learned that a function was continuous if the point existed, if the, here we can write them down, right? So your first step was that f of a existed, the limit of f of a as x approaches a also existed, and then if they were equal to each other. Oops, not exists. So the same thing is true for a function to be differentiable, but the only difference is that it would be about their derivative instead. So your derivative would have to exist, your limit of your derivative function would have to exist, and then your derivative would have to equal the limit. Now, in a graph, there are some very easy ways for you to determine whether or not a function is differentiable. Graphically, basically, it means that f has a well-defined non-vertical tangent line, i.e. the graph is smooth at x. There are some examples of when your function is not differentiable. So first of all, if your function is not continuous, then there's no way it can be differentiable. One of those fun sentences goes that all, differentiable functions are continuous. But one thing that doesn't necessarily have to be true is but all continuous, not all continuous functions, let's write functions correctly, are differentiable. So all differentiable functions are continuous, but not all we're going to try again. All differentiable functions are continuous, but not all continuous functions are differentiable. So basically, I like to, if you don't want to feel like remembering that phrase, the other way that you can remember it is that in the alphabet, when you start learning your letters, we learn the letter A, and then B, and then C, and then D, and so on and so forth. So when you're learning your alphabet, you can get to a continuous function without getting to a differentiable function, right? So I could hit the letter C before I get to the letter D. But there is no way when you're reading off the alphabet that you could get a differentiable function without it also being continuous first. So however you remember this is up to you. But basically it's saying that if you have a continuous function, it doesn't automatically make it differentiable. But if you have a differentiable function, it has to be continuous. And so one of the examples where a function is not differentiable is if it's not continuous. Like I can't take the derivative at 0 because there is no way, right? It has a discontinuity. So that would be another way you could ask this question. So when is a function not differentiable? You could ask, can I take the derivative at that point? Can I find the slope of the tangent line? So no way I could find the slope of the tangent line here. So then the other place that you might not have, or that your function would be not differentiable would be at a cusp. Because remember, if we're doing derivatives, that's their slope of your tangent line. So basically, if I'm coming from the left-hand side and I have my slope of my tangent line looks like it's -1, and then if I'm approaching from my right-hand side, the slope of my tangent line looks like it's +1, but we actually have no idea what happens at this point. Do I draw my slope this way? Do I draw my slope this way? Do I draw my slope this way? We don't know what's happening at that cusp, and so we would say that our function is not differentiable at any point you have a cusp. It also could be known as a corner. It could look something like this, or it could be a straight line like that as well. Okay, so basically anytime you have a cusp or a corner, your function is not differentiable. If it's got a discontinuity. It's not differentiable. And then the last place would be if it has a vertical tangent line. So if your graph goes vertical at a certain point, then we would say it's not differentiable because the tangent line slope here would be undefined, right? Horizontal lines have a slope of 0. So the derivative anywhere you have a horizontal line is 0, but the derivative anywhere you have a tangent line, or a vertical line, excuse me, is undefined because the slope of vertical lines is undefined. Okay. And then this is the theorem, or the another way of writing what we were doing up here, basically the difference between continuous and differentiable functions. So all differentiable functions are continuous, but not all continuous functions are differentiable. And now we're going to do a bunch of examples. It's going to be great. So in this problem, if f is a function defined above, then f prime of -1 is, and this is where you have to go through and you have to follow the same steps for continuity, but you have to do them with their derivatives. So I have to find f prime of -1 if it exists. I'll have to find the limit of f prime of x as x approaches -1 from the left-hand side and the right-hand side, because I have a piecewise function here. And then you'll have to see if they equal each other. Now, the first step in this would be to find f prime of x, right? And so if I'm going to do that, it'll be a piecewise function because I started off with a piecewise function. So f prime of x, well, what's the derivative of 2x plus 5? Well, the derivative of that would just be 2, and that would be for x values less than -1. And then what's the derivative of -x squared plus 6? Well, that would be -2x, and that's for values, x values greater than or equal to -1. And so now I can apply the same steps for continuity to my derivative, and that will determine whether or not my function, is differentiable at this point. So f prime of -1 would be if I actually plugged in -1. So I plug in -1, I get -2 times -1, so to give me a +2. All right. My left-hand limit, if I plug -1 into the left-hand side, well, no matter what, I get out 2. And then if I do it from the right-hand side, oh, same thing, get out 2. So 2 would be my derivative, because my actual derivative equals 2, and then my left hand and my right hand limits of my derivative equal 2 as well. All right, let's try another example. Let f be the function given above. What are the values of a and b for which f is differentiable at x equals 1? So let's go ahead and still set up our differentiability piece. So basically it's saying that f prime of -1, we want that to equal my left-hand limit and my right-hand limit. So this is already the right-hand limit, so, or excuse me, left-hand limit, so I will also write that. So I want these things to be equal. Oops, or I'm figuring out what value, what is happening, of a and b would make these things equal. And so when we're taught to do this with continuity, basically what you do is you make sure that these two pieces equal each other when you plug in this x value. So if we're going to do it for derivatives, though, you have to take the derivative first. So let's do that. So f prime of x would equal, derivative of x plus b would just be 1. And then that's for x less than or equal to 1. And then the derivative of ax squared. A is a constant, so if I find the derivative of ax squared, it'd actually be 2 times ax for x greater than 1. Lovely. And so now I want these things to be equal. I want my left-hand limit / my actual point to equal 2ax, but I want this to be true when my x value is equal to 1, so I can actually replace that with a 1. Awesome. So then if I go ahead and solve for a, we get that a is 1/2. Now you might be thinking, oh look, I can go find the a is 1/2. Oh, but there's lots of options for where a is 1/2. And that's when the play comes in that we're going to have to deal with b as well. And for b, we know something about this function automatically if we know where it's differentiable. We know that if our function is differentiable at x equals 1, when a equals 1/2, our function is also continuous because all differentiable functions are continuous. So what we can do is we can set just the original functions equal to each other. So my x plus b has to equal ax squared when x equals 1. And I know a because I solved a using the differentiable piece. So a equals 1/2. So I'll plug in all this information, and then that should just leave me b to solve for. So 1 plus b equals 1/2, 1 squared. So I'll get b equals negative 1/2, right? 1/2 minus 1. Beautiful. Okay. All right, let's go ahead. How many more of these do I got? 1, 2, oh, just 2? Perfect. All right, so this would be an example of a problem where they're, again, kind of comparing and contrasting the continuous and differentiable pieces. And so we're going to have to be able to deal with all of those all at once, and that's okay. So let f be the function given above. Which of the following statements are true about f? So the limit exists, the function is continuous, the function is differentiable. Well, let's go ahead and just check the first two pieces by checking continuity, because you have to do this anyway for continuity. So if my function is continuous, that means that f of 3 would have to exist. So what would f of 3 be? 3 plus 2 would be 5. Okay, check. And then my limit, let's do my left-hand limit and my right-hand limit. So my left-hand limit is going to be 5 as well. And then my right-hand limit will be, if I plug in 3 there, 12 minus 7, also 5. Excellent. So my limit exists, my function is continuous, and then the last step is to check if it's differentiable. So we do the same thing, but with the derivatives. So I'll find the derivative of this first, and then we check the same steps. So the derivative of the top would be 1 for x values less than or equal to 3, and then the derivative of the bottom would be 4 for x values greater than 3. And automatically, I can see that this would not be true, but let's just double check it. So f prime of 3 would be 1. My left-hand limit would also be 1, but then automatically, what's my right-hand limit going to be? Because they're just numbers, so I don't actually have to calculate anything. My right-hand limit would be 4. Fail. So our limit exists, our function is continuous, but it's not differentiable. So we would say 1 and 2 only. All right, last question. In this one, it says a graph of a function f is shown above. At which value of x is f continuous but not differentiable? So, for example, I notice right away that d and b have discontinuities, so I can actually cross those off because a clarification of the statement says we want to know where f is continuous but not differentiable. And so the only other places you have to check are a and c, and I notice at a that we have a cusp on our graph. So a would be the choice. A is where your function is continuous because there is a point there and your limit exists and they all seem to equal the same thing, but you have a cusp, which means you can't take the derivative there. Awesome. All right, so go ahead and practice with that and let me know if you have any questions.